So good morning everyone, my name is Alexis Joly. I'm a computer scientist at INRIA in the south of France. And it's my pleasure to present LifeCLEF, which is the lab of CLEF dedicated to biodiversity data. As a motivation of LifeCLEF, I have mentioned here the last report of the IPBES, which is the first critical assessment ever carried out by an intergovernmental body about the status of biodiversity on Earth and its importance for human foods and human safety in the upcoming years. And in this context, it is very important to develop new tools to improve the surveillance and the management of biodiversity. So in this regard, LifeCLEF is organized around 4 challenges, which are depicted here on this slide. And so the first one is PlantCLEF, which is related to image-based plant identification. The second one is BirdCLEF, which is related to bird sounds recognition. The third one is SnakeCLEF, related to snake species identification, and the last one is related to the prediction of species according to their environment and based on remote sensing images. So let's go into the details of these challenges, and starting with PlantCLEF. So PlantCLEF is a long-term evaluation of automated plant species identification since it started in 2011. And during the first years, it was mainly oriented towards improving identification on species for which we had a lot of data, so basically in Europe and in the US. But since 2019, we are concentrating on the most difficult species, which are the ones in tropical regions, such as the Amazonian rainforests, in which the biodiversity is the highest, but also for which we have much less data, and so the problem is much more complicated. And in particular, since last year, to identify the species, we are using the only materials that are sometimes available for the species, and that are herbarium sheets present in the collections of museums. And so the idea is to try to identify the species based on these herbarium sheets and the few pictures that are also available for the species. So, in other words, it is a cross-domain classification task, and to solve this task, we provide a training set, which is about 1,000 species in French Guiana. And for this species, we provide a very big data set of herbarium sheets, so actually more than 300,000 herbarium sheets, and only a much smaller set of field photographs that are aimed at helping the system to learn a transfer function between the herbarium sheets and the field photographs. And then we have a test set that is mostly composed of field photographs. So the idea is really to recognize plants in photographs based on the training sets on herbarium sheets. And the metric is the mean reciprocal rank of each of the observation in the test set. So here I present synthesis of the results that were achieved in 2020. And so as you can see, it's a very difficult task. And here we present the results for 2 parts of the test set, so either the whole test set or in orange, a subset of this test set that concern the most difficult species, that are the ones for which we have no photograph at all in the training set, only herbarium sheets, or very few photographs in the training set. And so as you can see, classical convolutional neural networks that just take the herbarium sheets and the pictures all together in the training set perform very poorly on this task. And even if you use additional training data found on the web or in other places, the performance remains very low. And so the only methods that were able to achieve better results were really focused on domain adaptation, that is specific neural networks for domain adaptation. And there were mostly two different methods. So one focused on training a common feeder space for the two domains, and one that was more focused on training a common metric for the herbarium space and the photograph space. And so as you see, this few-shot adversarial domain adaptation method achieved the best global results, but somehow the triplet loss was the one that succeeded the most to transfer knowledge from the two domains, as we can see on the orange bars, which concern the most difficult species. So in 2021, we will run the same challenge, and the main novelty will be that we will provide some additional data for the training of the models. And these data concern plant traits that we have crawled from Encyclopedia of Life. And so we have 5 traits that are fully complete for all the species in the training set. So even the ones for which we have very few data, we will have the knowledge of these traits. And so these traits are plant growth form, plant life form, trophic guile, woodiness, habitats, and all of them provide some information of the species that could improve transformance by allowing a better representation of feeders, thanks, for instance, to auxiliary losses in the network. All right. So now let's talk about the BirdCLEF task that is about bird call identification in soundscape recordings. And so the goal is to predict the list of species that are audible in a 5-second segment of a soundscape recording. And as for training data, we provide a large set of focal recordings, so with only one species recording, and this recording comes from the Xenocanto dataset, which is the largest citizen science initiative related to bird audio records. So this concerns about 400 species of birds in Costa Rica, Colombia, and United States. And now the test data is composed only of soundscapes. So in total, it is 13 hours of audio recordings on 4 different sites. And they are composed of very intense acoustic scenes with potentially many birds singing together. And so we also provide some entry-level tutorials and some codes to help new participants to quickly get results and progress more iteratively. So the rules is that you can only train the model on the focus recording, so the monospecies recordings. You don't have the right to use the validation set, the soundscape validation set, or the test set to train the model. And so any other publicly available data may be used, but must be declared. And also the top scoring participants must publish their code. So the metric is a F1 score, but that is computed for each chunk of 5 seconds and the average afterwards. And to encourage participation, we have 2 prizes for this, for the BirdCLEF challenge. So one that is a prize money because it's run on Kaggle in collaboration with Cornell University and with Google, and also we'll have an award for the best working node in the form of cloud credits on Microsoft Azure. So this prize is also available for all the challenges in LifeCLEF for the fourth one. So what is hard in this challenge, and the most difficult problem is that there is a significant shift in the acoustic domain between the focal recordings, so the monospecies recordings, which are of high quality and only contain one species, and the test data, which are composed of these many birds and overlapping sounds and with a much more significant level of noise. And in addition to this main task, there will be a second subtask for the first year, this year, and that is basically the same goal, so to predict the list of species audible in 5-second segments, but here it's based on stereo recordings, which makes the main difference. And so this data provided from another site in the south of France. And so the idea is that this stereo could be used for additional analyses, such as source separation, to get a better separation of the birds vocalizing in the soundscapes. So now let's talk about the GeoLifeCLEF challenge, which is organized jointly with Caltech and INRIA. And so here the task is not to recognize species, but rather to predict the list of species that are the most likely to be observed in a given environment, so at a given place. And the idea is that we provide a geolocation and some data associated to this location, so remote sensing data, environmental rasters, and so the goal is to predict the species that are likely to be observed there. And this is the first publicly available data set to pair remote sensing imagery with a so huge amount of species observations. And so in particular, these observations come from two major citizen science initiatives, which are iNaturalist and PlantNet. And so all these occurrences were paired with high resolution covariates. So remote sensing covariates are mainly RGB, infrared, altitudes, and the land use. And we also provide some coarse covariates more related to the environment, such as climate data or soil variables. So then all the 2 million occurrences were split, and to avoid just training by position and to really measure the ability of the models to generalize to other places, the split between the train and the test sets is based on a spatial block holdouts on a 5-kilometer grid. And the metric to evaluate the runs is the top 30 accuracy, and also the average 30 accuracy, which is a generalization of that, where we use a threshold on the probabilities so that on average there are 30 results per prediction. So the challenge was already run in 2020, but only 2 participants succeeded in submitting run, and only 1 with correct results. And so to increase the participation in 2021, several improvements or extensions were added. So the first thing is that the challenge will be jointly organized with the fine-grained visual categorization workshop, which is run since about 10 years now in the context of the CVPR conference. And also the challenge will be hosted on Kaggle. And since the challenge is quite hard to start with because of the volume of data and the different nature of this challenge compared to what is existing, we also provide a lot of resources this year, such as Python codes for data loading, data loaders, data visualization, codes for metric computation, and also some baseline models and scripts to train them. And also we provided some additional data formats that are more common to computer scientists, such as JPEG, TIFF, or CSV. So now we arrive to our last challenge, which is the LifeCLEF challenge. And here the goal is to predict snake species based on pictures, but also on the location context. So it's not the precise localization, it's the country or continent level location context. And so the motivation of this challenge is that over 500,000 of victims die each year from venomous snake bite. And so there is a need to have tools that helps with the identification of the snakes and to guide the treatment of the first responders. So the task will include more than 400,000 images of almost 800 species of snakes, and so which come from diverse sources such as iNaturalist, HelpMapper, Flickr. And so to illustrate the difficulty of the problem, we can see here on the right, this is 4 individual snakes of the same species, whereas what you see on the left is individual snakes of 4 different species. And so as you see, the intra-class variability can be very high, and on the opposite, some species can be very similar, some different species can be very similar, so which illustrate the difficulty of the problem. So in 2020, the challenge was already run, and so on average there were some pretty good accuracy, so with the best run with 88% of accuracy at the species level. But as you can see on the bottom right plot, there is a lot of heterogeneity between the countries, and so there are countries for which species are very illustrated in data set and for which you have very high accuracy, but there is also a large majority of countries for which the performance is much lower. And so the main target of the 2021 edition will be to focus on the country-wise performance instead of the overall performance. And so to really encourage also recognizing species from this countries where there is less data. So I would like to thank all the organizers of LifeCLEF, and I provide here the list and the contacts. The main entry points, if you're interested in participating or to get more information about LifeCLEF, is this URL, lifeclef.org. And I thank you a lot for your attention, and please contact us if you want more information.